Okay, this is going to be a video on the law of sines. This might be a little long, so let's dig into it. Basically, excuse me, what we're going for here is we can now solve for triangles that are oblique or non-right triangles, because before, when we've been using our sines and cosines and whatnot, that's been for all right triangles. So what I've done here is I've taken this oblique triangle ABC and I've dropped a height, let's call that H. And so it says, how can we find the height in two different ways? So let's use our sine of B, which is 45, is going to be equal to our opposite side, our H, our height, over 7.1. And when you crank that out, you get 5.02. Now, a different way, we could say sine of our 68.2 is going to be equal to our H over 5.41. And unsurprisingly, we end up with 5.02. So we got two ways to get to the same thing. So how can we kind of describe this generally? Well, I said that the sine of angle B times the side C here, 7.1, was equal to the height. And I also said the height, so right here, the height was sine of angle C times the side B. That was equal to the height. So kind of condensing these, we can say, since they're both equal to height, they're equal to each other. So B sine C equals C sine B. Or another way, and the most likely the way you will see this written, the law of sines written, is doing a little bit of algebra. Sine B over side B, sine of angle C over side C, and if you add a third side, the sine of angle A over side A. So you got this nice, all the sides and their angles. So this angle is opposite that side, this angle B is opposite side B. So you got all the B's on the same side, but you get this nice kind of equality here. So this last triangle, all of your angles are acute. But what happens if we've got the height that's outside the triangle, meaning that we have some sort of obtuse angle like this 123.7 here? How are we going to do that? So let's drop a height there, and let's say, how are we going to find the height? So let's start with this 20.6 degrees. It's equal to our opposite H over our hypotenuse, or over our hypotenuse of 8.5. So that shakes out to, when you multiply over the 8.5, 2.99. Now it says let's go ahead and find this length of AB, because that's going to be important. So how would we go about doing that? Well, the thing we need to note here is that 180, sorry, I got a lot of kind of external noise going on here. 180 minus 123.7 is going to be equal to 56.3. So now I know this one is 56.3. So that gives me a way to solve for this side AB. So let's go ahead and do that. The sine of 56.3 is equal to, because I now know this height is 2.99 over this side right here. This, I guess that technically is side C. So C is equal to, when you do that division, you get 3.59. And again, these are just things you can plug in your calculator. I did it beforehand. So does the equation still work? Does this B sine C equals C sine B still work for this? Well, let's try it out. So we've got the side 8.5, and we've got my angle. So I'm doing side B sine of C, which is 20.6 degrees. that is going to equal 2.99. Again, you can plug that in your calculator. And that should equal this B sine C. Or excuse me, sorry, C sine B. And because our angle B here is our big obtuse one, and that's the one we're trying to prove is equal. And we just figured out that this other side right here is 3.59 times the sine. So I wrote that kind of backwards. And that also is equal to 2.99. So yes, check. This does in fact work for these triangles, and this should make sense. And this is a super important concept to understand. The reason that we can do 180 degrees minus that angle right here and still have this work is because of our unit circle. So if I say pi over 6, I can subtract, so another way to say 180 degrees is pi. I could say pi minus that. So pi, let's take pi over 6 in this example. So pi minus pi over 6 is going to be 5 pi over 6. So if we pull out our unit circle, the sine of 5 pi over 6 is going to be 1/2, and the sine of pi over 6 is also going to be 1/2. We're just switching quadrants. So the reason that we can take this sine here, the sine of 56.3, where we did that right here, the reason that equals 2.99, and our sine of 123.7 is going to equal 2.99. The reason that all works is because all you're doing is going from quadrant, okay, let's not do that. You're going from quadrant 1 to quadrant number 2. So that is the fundamental underpinning of why that works. I'm going to leave y'all to solve this one. You've got a couple angles and a side. I'm sure using your ratios that I just gave you, you can do that. And this one I'm not going to cover. I will cover these two. So B and C. Can we solve it with the law of sines? So let's just kind of plug it in. Let's say sine of 93. And then we don't have a side B. We don't have that. Is going to be equal to, well, we have another side, but we don't have another angle. So that's going to leave us with some sort of sine of some unknown angle over, maybe let's choose side C. So this would leave us with the sine of C. So we've got a B and a C. We got too many variables, so we can't solve that. And maybe you're thinking, okay, maybe this C1, we got only one side here, and we got a couple angles, and the kind of key, if you're trying to do these quickly, the key here, the reason this one, you'll end up, once you solve this, you realize that it's important to have a angle and its kind of matching side over here. And we don't have that here, but we can find it with a little knowledge that 180 degrees makes a triangle. So we've got this 61 and 30 for a total of 91 degrees, which leaves us with a remaining 89 here. So we can then solve this because we have an angle and its adjacent side, and then these two start to look pretty similar. So again, another one for y'all to work out here. But this is the real meat here, is what's called the ambiguous case. So the ambiguous case is when you're given a side, and an angle. So we've got our angle here, and we've got two sides. So I'm going to go ahead and draw this, and I'm going to rename these in a second. Let's draw it like that. So we've got this angle of 45 degrees, that's angle A, and then we've got this side here of, I'm going to call that one C, call this one B, and then this is 4.8 centimeters, that's going to be side B, and this 6 centimeters is going to be our side A. So you'll start to notice that this looks a little different. I'm going to set up this equation. We've got our sine of 45 degrees over our opposite side, which is 6 centimeters, is going to be equal to our sine of B over our opposite side of 4.8. So I'm going to move this around, move this 4.8 over. So we've got this 4.8 sine of 45 degrees over 6, which is just a number, is equal to the sine of this angle B. So in order to solve for this B, we're going to have to take a sine inverse because we're given the ratio we have, and we need to find the angle. So angle is in question. So we'll have to take the inverse sine of all this comes down to, let's see, gotta reference my notes so I don't have to calculate this, 0.565. And that gives us an angle of 34.45. So we've got this 34.45 here. And so we can solve for the last angle. We got 180 minus the rest of that. But let's see here if we could potentially have two triangles. Just humor me a second. So we got 180 minus 34.45 gives us 180 minus 34.45 gives us 145.55. Now, the reason I did that is the same reason here in this unit circle that I drew you somewhere. The same reason that you can have two answers to this. You're in quadrant 1 or quadrant 2. So it's really important to note is when you're taking the inverse sine, you're not quite sure whether it's going to be in quadrant 1 or quadrant 2, which is why I took 180 minus the angle that we initially found with our inverse sine, this 34.45, and I see that it's 145.55. Now, once you get that, it's important to check, okay, is that even possible? Is that something I can do? And the answer is no, because 145 plus this other angle of 45 already goes over our limit of 180 degrees for a triangle. So this is the only solution. Now, I will quickly go through these next two, in that we generally solve this the same way, so I'm not going to go through all of this, but the way that the work shakes out is 2 over the sine of 45 degrees, because we stick with the same angle, is equal to 4.8 over the sine of this other side. So we again end up with this inverse sine. We're going to end up with inverse sine of B, of this angle B, is going to be equal to 1.7. Now we should stop ourselves right there because we know that the the range of our sine function is -1 to 1. So this is going to fall strictly outside of our range of our function. So that's going to be an error, and this is in fact not a triangle. So no triangle possible. Using this same kind of process, I'm going to leave y'all to do number 10, keeping in mind what I did here. I did this 180 minus the angle that we found with the inverse sine, and then checked to see if that would fit in the triangle. So why don't y'all go ahead and try to find the angle using the same process, and then see if the complement of that angle, 180 minus that angle, fits in there as well. And then this number 11, why is it not straightforward, is because of that inverse sine that I just described, that it could fall in quadrant 1. Answer isn't a valid answer, as is quadrant 2. Okay, I'm going to keep it under 15 minutes and stop it there.